So let's go ahead and discuss 14.3. So again, a vector valued function. Let's discuss the two dimension case. Well, so this is going to describe the position of a particle at a given value of t at any time. And while the velocity and the acceleration are all, recall from Calc 1 that those are also in a way they might not have told you that they were vector quantities because we didn't discuss anything about vectors in Calc 1, but it's in this case we will discuss them as vectors. And the velocity is nothing other than the first derivative, and the acceleration is nothing other than the second derivative of the vector valued function. In the same way as in Calc 1, the first few applications of for rates of change, first derivative that's the velocity, second derivative the acceleration. But in this case, let's pay special attention to the speed, because speed is not the same as a velocity, because velocity has a direction as opposed to the speed, which is just the magnitude of that velocity. And in this case, notice the magnitude function here is the square root of the sums of the squares, so in this case the derivatives of the components. Alright, that's how we're going to compute the speed. And of course these definitions are the same and can be extended for vector valued functions in the space. Alright, so let's have a look at one example. So let's find the velocity, the acceleration vector, and find the speed for a particle moving along the curve described by r of t, 1 over square root of ti, 2t plus 1j, and te to the t minus 4k. So, before getting the velocity and the acceleration vector, I'm going to rewrite this vector valued function because we cannot just differentiate 1 over the square root of t. So let's rewrite it using negative exponents, and I'm going to switch to component form. So that's going to be t to the negative 1/2, 2t plus 1, and te to the t minus 4. Okay. This way we can easily take the derivative of the first term. The other two terms, it's no big deal. So let's find r prime. So let's just differentiate each component in the same way we did it in the previous section. Use any differentiation rule that applies. So in this case, the general power rule, that's going to be negative 1/2 t to the negative 3/2. The derivative of 2t plus 1, that's just 2. And the derivative of te to the t minus 4. Any ideas on how to differentiate that one? Product rule, right? So product rule, let's write down what the product rule is again. So the derivative of a product uv, so that's u prime v plus v prime u. That is the derivative of the first term times the second plus the derivative of the second term times the first term. Alright, so the derivative of the first term, which is 1, times the exponential, is just the exponential t minus 4, plus the derivative of the exponential, which in this case is itself, e to the t minus 1. No chain rule needed here because the derivative of t minus 4 and the exponent is just 1, right? So that times simply t. Okay? So all I'm going to do here is rewrite this t in front of the exponent, of the exponential. And this is the velocity vector. Let me actually label it as v of t. So we'll no longer just call them r prime or r double prime. These are going to be actually v, the vector v. And how about we find the acceleration vector? That's just the second derivative, right? That's r double prime And well, the second derivative over here, again, general power rule, that's negative 3 halves times a half. Is that a positive 3/4? T to the negative 3 halves. So minus 1, isn't that a negative 5 halves? What's the derivative of 2? 0. And the derivative of this exponential function. Okay, so we may need another product rule. Well, number 1, let's do one term at a time. What's the derivative of this exponential? The same thing, right? E to the t minus 1, no chain rule because the derivative is 1. And what about the derivative of this product? Isn't it this whole thing right here? And that'll be t e to the t minus 4 plus e to the t minus 4. But rather than writing this twice, how about we put a coefficient of 2 in front of it? Alright? So that's the acceleration vector. And they're also asking us to find the speed, right? The speed function. In this case, the speed is going to be not a vector, but rather it's going to be a scalar. And in this case, the speed that's the magnitude of the vector of the velocity vector, which in this case is the square root of the quantity negative 1/2 t to the negative 3 halves quantity squared plus the square of the y component, and this one is just 2 squared, plus in this case that's going to be the square of this third component, which is this crazy looking function. That's e to the t minus 4 plus t e to the t minus 4 quantity squared. Alright, notice this is not a vector, it's actually a scalar. And well, there's not much to simplify over here other than maybe turning this negative 1/2 squared as 1/4. Negative 3 halves quantity squared, isn't that going to be negative 3? And then that's 4. And well, I mean, we could expand this binomial square, but really it's just going to turn into madness here. So let's just leave it like this. E to the t minus 4 plus t e to the t minus 4 quantity squared. And that's the speed function. That's the magnitude. Alright, well, so we already got the algebraic expressions for each corresponding property they're asking us to describe. Now they are asking us to find the velocity, the acceleration, and the speed when t equals 1. So all we're going to do here is plug in 1 for each of these three quantities: the velocity, the acceleration, and the speed function. Let's go ahead and do one at a time. So let's see. So V evaluated at 1. Okay, so whatever we see the letter T on the velocity vector, let me highlight just so you can see what I'm doing here. So it's going to be here, here, and here, or also here. All right. So, what is 1 to the negative 3 halves? Isn't that just 1 times negative 1/2? It's going to be negative 1/2, comma. Here it's just going to be 2 because there's no variable t to plug in the value of 1, comma. E to the 1 minus 4, isn't that going to be negative 3? E to the negative 3 plus 1 times e to the negative 3 also. But if we combine these two numbers together, isn't that the same as saying negative 1/2 to 2 e to the negative 3? Alright? So that's the velocity vector. What about the acceleration vector? For the acceleration vector, that's A evaluated at 1 also. And well, in this case, we are plugging in 1 at every instance of t in our acceleration vector. Okay, and I'm highlighting them just so you can see where am I plugging this in. So this is going to be, well, 1 to the negative 5/2 times 3/4, that's simply 3/4, comma, 0. And, well, so e to the 1 minus 4, isn't that again e to the negative 3? And another e to the negative 3 times 1, that's going to be 2 plus 1, isn't that, well, let me write them all. 2e to the negative 3 plus 1 times e to the negative 3, that reduces to a, oh, not 8, actually, that's 3/4, 0, and 3 e to the negative 3. All right? So that's the velocity and then the acceleration. And now let's find the speed. All right? Okay, so there's a couple of ways to find the speed. Number one, you could okay, speed will be the absolute value of the velocity vector evaluated at 1. And there's a couple of ways to do it. Either you simply take the magnitude of this vector, which we already had, which I believe is the most simpler way to do it, or plug in 1 to this humongous expression. Either way, you should get the same thing, because, I mean, where did that velocity come from? From this, or actually, where is this magnitude going to come from? Taking the square root of all these symbolic numbers, all we're going to do is square them, but we already have evaluations at 1 for that humongous expression, so I'm going to take advantage of this instead. So that's going to be negative 1/2 squared plus 2 squared plus 2 e to the negative 3 quantity squared. All right? And after combining this, I'll just give you the answer. The speed should be 17/4 plus 4 e to the negative 6. Which we can just use a graphing calculator to see what's roughly the speed. But I mean, typically we would do that if we have an actual physical context, I mean a word problem, so we can have an idea of what the speed is. In a case like this, which is just symbolic, well, we just leave it in exact form. So MyMATLAB may ask you to reduce to some decimals, to 2 decimals or 3 decimals, or just the exact way. Okay, what else do we have? The position vector r of t equals to t squared I plus t. J describes the path of an object moving in the xy plane. So let's go back to the xy plane, not the xyz space. And sketch the graph of the path and sketch the velocity and acceleration vectors at the point 4, 2. Well, so it's actually going to be a very similar problem, but in this case we're given different information. We're not given the actual value of t. We're given a point. We will have to figure out what is the time where the particle is at the point 4, 2. And well, number one, of course we can use our parametric form in our graphing calculator, but how about we do a table in this case? So for different values of t, we're going to get x and y. All right? And well, of course, it doesn't say any limitations about the domain or the piece of the piece of the function that we want to graph. So I'm just going to go 0, 1, 2, and 3. And well, what do we do? Plug in these values of t at each component of the vector valued function. So that's going to be okay. Let me do the squares first. 0 squared is 0, 1 squared is 1, 2 squared is 4, and 3 squared is 9. And for the y component of the vector, we have simply t, all right? So we just substitute 0, 1, 2, and 3. And to graph the path along the particle is traveling to, all we do is plug this as order pairs. So 0, 0, 1, 1, 4, 2, and 9, 3. And in this case, it's important to also denote the direction of this function. So, and I'm going to use a different color for that. It's going in this direction, all right? From left to right. Actually, that's what you're going to get if you do it in your graphing calculator. You're going to see the graph being drawn in that direction. And that's what actually these order pairs pretty much depict. But of course, I mean, this can also go in the negative direction this way. All right? Although we really don't care about that part, because we really care about the acceleration and the velocity vectors at the point 4, 2, not at a value of t. We need to figure out what's that value of t. And there's a couple of ways to figure out the value of t at which we are at that point. Number one, set the two equations, the x equation equal to 4 and the y equation equal to 2. That's number one. Or just use the information from the table. Don't we have that piece of information? So when t equals to 2, the particle is at the point 4, 2. So you might want to just t equals to 2 from table. All right. Well, they're asking us to find and actually graph the velocity vector and the acceleration vector. But to get those vectors, we need to find the velocity function and the acceleration function. So the velocity function, which is v of t, that is the derivative of the given function. So what's the derivative of t squared? That's just 2t, and the derivative of t, which is 1. And then the acceleration vector, which is the second derivative of the vector function, that's 2, 0. All right. Now we need to find the velocity vector when t equals to 2. That is the value of t at which the particle is at the point 4, 2. And so that's, in this case, well, plug in 2 times 2, 1, and that's going to give us the vector 4, 1. And for the acceleration vector, notice there's actually no variable t, but we still denote a of 2. That's simply the vector 2, 0. All right, there's really no t's to plug in. Okay, so let me highlight them using different colors. Acceleration and the velocity vector. All right, so I'm going to draw the velocity vector at this point, at the point 4, 2. So from here, start here, and from there for the velocity vector, which is 4, 1, I'm going to count 1, 2, 3, 4 units to the right and 1 unit up. And that's the velocity vector. And for the acceleration vector, Starting at this same point, the point 4, 2, I'm going to count 2 units to the right and 0 units either up or down, so just 2 units to the right. So in this case, that's just 2 units, and that's the acceleration vector. All right. In 2 dimensions, it's doable, as you can tell, but not in 3 dimensions. Imagine trying to do this in 3 dimensions. It's not unless we have some like some applet like the one I showed you. But I don't think the applet I showed you can also graph its tangent and acceleration vector. Maybe I should look for one, and hopefully I can find it. All right, so for the next example,